Okay, this is MAC 1105 and we are in section 4.4. In this section, we're going to be learning how to finish up your set of equation solving skills, and we're going to move on to solving an exponential type equation. There are several methods for solving an exponential equation depending on the form of the equation that they give you. So what you're seeing in, let's see, from 1 all the way to 8. I guess I can put this right here. Numbers 1 through 8, you're going to use a technique because it's possible to use this technique. I would always use this technique when they make this available to you, where you try to make the bases the same on both sides by rewriting them. Okay, and this is what I mean. Like for instance, with this 2 to the x, the 16 that is written on the other side, and then I'll show you the property that you're going to use to finish the problem, you can write a 16 using 2's. So whenever you have the opportunity to write both sides using the same base, take that approach. Okay, you're going to write both sides using the same base. You can always use your calculator to help you with this part, but on the left you have 2 to the x, that's already in base and power form, and then you want to write the 16 in base and power form, only using the same base as this. So this would be 2 to the 4th. Okay, and then from there, the concept is that the only way two exponential expressions can be equal, these are both exponential expressions, is if their bases are equal, which you can already see that they are, as well as their exponents. So at that point, what you're going to be doing is you're going to concentrate on just these exponents right here. So the x, and you're going to make a separate equation to finish the problem out of those exponents. Again, two exponential expressions can only be equal when their bases are equal as well as their exponents. So you're going to take the exponents, set them equal. If there's any further solving to do at this point, you'll do so, but there isn't in this case. So x is equal to 4. And you are going to use this same approach because they've made it available to you. We'll see if there's any problems that we hit a wall with, but you should be able to use this approach in numbers 1 through 8. Okay, when you have to use your calculator, use your calculator. Like for instance, in this problem, you see that one side has a base of 9. Therefore, see if possibly you can rewrite this number 6561 using a base of 9. Get in your calculator, mess around with some various powers of 9 until you see which one produces 6561, 6,561. Okay, so let's see. Let me get in my calculator. And it is 9 to the 4th. Okay, then using the property that I talked about in number 1, two exponential expressions can only be equal if their bases as well as their powers are equal. So now all you're going to do is continue the problem with just these exponents. So you're going to write a separate equation because you can already see that the bases are equal. Now you have to make those exponents equal, which are 2x minus 8 and 4. And now continue to solve it. Bring the 8 over here. And you'll end up having 2x equal to 12. And then divide both sides by 2. And you'll have x equal to 6. Okay, likewise on this problem, you're going to want to use your calculator possibly to mess around with the with both of these numbers depending on where your skills are at with powers. But notice that when we get to number 3, at least in numbers 1 and 2, one of the sides served as a hint as to what you should rewrite the other side. Like this gave me a hint to be using 2's, 2 to some power to get a 16. This gave me a hint that if this base was a 9, maybe I should use a 9 here. I mean, it's possible that I would have had to change both of these bases to 3, but here you don't have any hint, because try raising 30. If you think this is the power this is the base that you're going to be able to raise to a power to get 128, try doing that in your calculator. 32 to what power would give you 128? Nothing. So that means that you got to break both of these down. You have to look for some smaller base and a power to go with it that creates a 32 as well as a 128. I would start by working on the smaller number. Like for instance, 32 can be written in power form using 2's. 2 to the 5th is 32. So there's your 32 raised to a power of x. And then if you don't remember this rule, whenever you have 2 powers, you're raising one power to yet another power on the outside, you mingle these 2 powers by multiplying. This is called the power to a power rule. You multiply. So this 32 to the x becomes 2 to the 5x. Those 2 powers mingle by way of a multiplication sign. Now, since my base is 2 on the left, that kind of gives me an idea that I should be writing the 128 also using 2's. So your job is just to get into your calculator and figure out 2 to what power is going to give you a 128. You can just check that out, mess around with a few numbers to see what power you have to raise it to. So it's 2 to the 7th is what works there. Once you get the bases matching, then you can finish the problem by just using the exponents, because there's no way for these 2 expressions to be equal unless the bases match as well as the exponents. So you're going to find out what makes these match. In other words, what makes them equal. You have a little equation here you can solve once you do that, and your answer turns out to be 7/5. Okay, moving to number 4. Same situation in number 4 as we had here. It's 27. You cannot raise a 27 to any power to get an 81, but you could try going smaller, rewriting both of these numbers using a smaller base. Now I know you can write a 27 using 3's. So 3 to the 3rd power is 27. So there's your 27. But the 27 already had a power. If you want to mingle these 2 powers together, you need to multiply them. Okay, so that's going to be your left side, 3 to the 3x. On the other side, you had an 81, and that can be rewritten using 3's as well. I believe it's 3 to the 4th is 81. And you can always check that in your calculator. And it is, before you go on with the problem, so you're looking at this problem right now. Bases are the same, therefore you just have to worry about what makes the exponents the same. So you create this separate little equation with just the exponents and you solve. And these solutions that you're getting, you can actually check them in your calculator. If you wanted to, you could go and put 4/3 right in there, but you'd have to put a parenthesis around it if you were going to enter it in your calculator. But anything you're getting means that it works in the original problem to make this statement true. So if you went 27 raised to a power of 4/3, putting a parenthesis around the 4/3, you would get an 81. Any of these can be checked in the, in the calculator. Likewise with this one. If you put the 7/5 here, 32 raised to 7/5, as long as you put a parenthesis around it, will be equal to 128. Okay, number 5. Number 5, here you can see that this base, you can't break it down any smaller than that. That means that's an excellent hint as to what should be happening here. This is what you're looking at this point. You got a 5 raised to a power of 4 minus x on the left. On the right, you have 1 over 5 cubed. You want to be trying to use a base of 5 to some power. 5 cubed is 125. If you want this fraction to go away so that you can continue the problem, it's 5 to the 4 minus x on the left, and anything where the power expression's in the denominator, you can get rid of the fraction and just write it as 5 to the negative 3. Okay, once you get to this part, you got the bases matching, and you just have to work with the exponents, which are 4 minus x on the left and negative 3 on the right. And then you continue to solve that. Bring the 4 over here. That'll leave you with negative x. Don't forget to drop that negative in front. And a negative 7 on the right. Then divide that negative 1 right off. And you will have x is equal to positive 7. Okay, that's numbers 1 through 5. Here again, giving you more practice. I think this is the third one that we're doing here. Although we can make this simpler. We can get rid of the radical altogether by just saying this is 1 over 2, because square root of 4 is just 2. So let's just look at that as 1/2. So basically what you're seeing over here on the bottom, this is 1 over 2 to the first power. If you don't want to write this in fraction form, you can float this to the top, and it is said to be 2 to the negative 1. Now, if this has a base of 2, it is likely that the 256 can be written as a base of 2. So get in your calculator and see 2 to what power is 256. Okay, so it's 2 to the 8th. So in place of the 256, I'll write 2 to the 8th. That represents my 256, and that 256 is being raised to yet another power. If I mingle these two powers, I simply multiply them, and that would be 2 to the 8x is equal to 2 to the negative 1. Okay, bases are the same. Now just work with the powers. Okay, so only using the powers at this point to create the separate equation and solve. Okay, and x is equal to negative 1/8. And number 7, problem number 7, let's see. I believe both of these you can make out of 4s. But you could also make that out of 16. I just tried a 16 because I like to, see if I can use the base that's right there. And if that doesn't work, I try to break that down smaller. If you go 16 squared in your calculator, you do get 256. So this side already has a 16. And the other side can be written as the 256. One way to write that is 16 squared. And then the 256, there's your 256 right there, had a power of x minus 2. Okay, so when you continue with this problem, you almost are there. You want to mingle this power with this power, multiply the two powers together, so it would be 16 to the 2x, and then 2 times, you're multiplying it by both of these items, minus 4. So 2 times x, 2x, 2 times negative 2, negative 4. This one already is 16 to the x plus 6, and now you have this problem so that the bases are the same, and therefore finish the problem by setting the exponents equal. Because you need to know what makes those exponents equal in order for these two expressions to be equal. Okay, and then solve. You can bring the x over here. That'll give you 1x minus 4 with a 6 right here. And then you can bring the negative 4 to this side. That'll give you x equal to 10. That's your final answer. Okay, that's 1 through 7. There's quite a few problems in this section. They start to get very repetitive, but just to give you a solid foundation to start with, let's go ahead and do number 8 as well. Okay, again, one of the things that keeps popping up, this is probably the third one that's like this, you have a fraction, and those things can be written in power form. You want to be writing things in power form for numbers 1 through 8. So this is e to the x plus 2. That's already in base and power form. And then this e to the first degree here can be written as e to the negative 1, since that expression is occurring in the denominator. Once the bases are the same, as in numbers 1 through 7, you no longer need them because you'll only be working with the exponents at that point. And solve that. Bring this 2 over here, and you have x equal to negative 3. Okay, when you can no longer do this, which is the case once we get to these problems here, 9, 10, and 11, and possibly ones on the next page, there's no way for you to write 10 in power form. There's no number raised to any power that's going to give you a 10. So you can't break that down any smaller. And yet you also can't just use it the way it is. You can't go 10 to some power and get 3.24. So that suggests that there's a whole nother method that needs to be used here. The dilemma that I just explained here is present in these problems as well. You can't use this and say e to some power is 16.04 because you would never get 16.04, and the e doesn't break down. Likewise here. You can't go 5 to any power and get a 127. So there's no way to write both sides with the same base for any of these problems. So in that case, what you're going to do is you're going to take the log of each side, because one way to bring that power, that exponential power out of the air, is to take the log of both sides. So when you can't rewrite with a common base, unable to do that now as I was able to do it in 1 through 8, try taking the log of both sides. And that might either be the common log or it might be the natural log, depending on what this base is here. Like here, common log would work well. Since this has an e, natural log would work well. And that's because you can get the inverse property to work if you choose the right kind of log to take. When you take the log of both sides. I wrote that word twice. Let me get that out of there. Okay. So in this problem, I'm going to take the log of the side that has the 10 to the x. And if you take the log of one side, you have to take the log of the other side. This is where you're going to want to get in here and use your calculator. Now this is, when you're doing, these are called common logs. It is automatically said to be a 10 when you're doing common logs. Your calculator will do calculations for you in base 10. But what you have going on right here is the inverse property. When this matches this, they take each other out. This was in the last two sections, 4.3 and 4.2. Take the word log with it. And this entire expression is equal to whatever's in the exponential position, which is x. I'll continue right here. So the left side simplifies to x, and then this you're going to get in the calculator. Whereas this is the inverse property from section 4.3. So get your calculator involved there. You're going to push the LOG key, not the LN key, of 3.24. I didn't clear my calculator, so log of 3.24, close. I got 0.5105. I don't know what it says to round to. Decimal approximation. Round to 2 decimal places. Okay, so this would be 0.51. Okay, so the solution set is expressed in terms of common logarithms. The solution set is, now you that would be this answer. This is the calculator answer. And if you're going to give the answer in terms of logarithms, then you could, I mean, when they say give the solution in terms of logarithms, you're writing what it looked like right before you entered it in the calculator. So log of 3.24 would be that answer. Okay, let's move on to the next page, number 10. Okay, here you're going to, again, try to knock that x out of the air. You can't rewrite these bases the same because it's impossible. This works better with natural log, so you're going to take the natural log of this side and the natural log of this side. Natural logs have a base of e, which you can write the e or not, but in this case I think it's beneficial on the left side. So you could see that that e cancels with that e, takes the word log with it. Only thing that's left on the left-hand side is an x. And then on the right, you have ln, you don't have to write the e, of 16.04. So that would be that answer right there. And then when it says use a calculator to obtain a decimal approximation, round to 2 decimal places, then put it in your calculator. Make sure to press the ln, natural log key this time. So this is ln of 16.04. And I got 2.78 when you round it to 2 decimal places. Okay, moving to number 11. Okay, here you could either use, express the solution of natural logarithms or common logarithms. They're giving you an option, as I was commenting in an earlier section, that some of these you could use either one to get the answer. Now, if it was an E, I would definitely use natural logs because it just lends itself to that type of log. It'll make the simplifying easier. But when it's not an E, then you can just use log, or you can use ln. Okay, so if I took log of both sides, it would be log of 5 to the x, which is equal to log of 127. So all I did is take the log of both sides. Then I'm going to use some properties that I learned in the last section. And that's when you basically have 3 levels, because if this is a log, this is base 10. So that's first level, second level, third level. That exponential in the third level can be swung right out front to become the coefficient. So now my left side is x times log of 5, and you can write that base 10 or not. And then over here it's log of 27 of 127. In any event, you want to get the x by itself. So what you're going to do is, I'll put it up here so I have a little more room to work with it. It's x times log of 5 and then log of 127. Again, you have the option of putting that 10. I would put it there if I wanted to show myself using the inverse, but you don't really have to. I want to get rid of this log of 5 because I want to isolate my x. In other words, I want to solve for x. So I divide both sides by log of 5. That cancels. And then that's your answer right now when it's in log form. Okay, the solution set expressed in terms of logs. Use comma to separate answers as needed. Simplify your answers. So this would be log of 127 over log of 5. Okay, now use a calculator. You're going to press into your calculator log of 127. Divided by log of 5. Call my calculator up again. I don't know how I got rid of that. Okay, so I'll just write what I'm getting at each stage. This is 2.1038. If you're going to show your work at each stage, hang on to at least 4 decimals for each of your numbers. And then log of 5. .6990. And then if you want to go for the final answer, it would be top divided by bottom. And I got 3 point, and then you are rounding to 2 decimal places again. So that would be just 3.0. Or actually, no, 3.01, excuse me, because it's 3.009, so 3.01. Okay, that's number 11. Okay, this one, I think what I would do in this case is I want to take the natural log of both sides because the inverse property will work, but before you take the natural log of an expression that has an e, you want to get rid of the coefficient first. So I would divide by 7 on both sides. That'll make the 7's cancel, and you'll be looking at this. E to the x is equal to 71 over 7. Then you could take the natural log of both sides. You could take the natural log of this side, natural log of this side. So here what's going to happen is, because natural logs can only have base e, this augment cancels with the base, taking the log with it, and down comes the x. And then what you have on the other side is ln of 71 over 7. So in log form, you would give the answer like that. And if you're going to get a decimal approximation to 2 places, then you got to put it in your calculator. So this would be natural log of 71 divided by 7. And I got 2.32. When you give your answer like this, with the logs still in it, that's what we call an exact answer. This is just an approximate answer. That's why it says give an approximate decimal approximation. Okay, this one. The term that you're going to work on, that you're going to take the log of on both sides, you want to try and strip it clean of any leading coefficients, as I did here, or if there's anything added or subtracted from it, you want to move that before you take the natural log of both sides, as I'm going to in this case. So here I'd have to add 7, and then you would have e to the 5x minus 2 is equal to 21,439. 21,439 after you add 7 to both sides. So now you have e to a power and then just a number. If you want to knock this down from its exponential position, you can just use ln of both sides. ln here, ln here. The base of an ln is e, and I wrote it here just so you could see that the augment and the base match, therefore they take each other out, take the word log with it, and down comes the entire x expression, 5x minus 2. So that's what you have on the left. And then on the right, you would do a calculator deal. But you're not ready for that yet because they want you to give the answer with the logarithms still in there. So let's leave it like this for a minute. Get it all ready for the calculator by isolating all the way down to x. So that means we're going to be adding 2. Now this belongs to this right now. We're going to be adding 2 to bring this over here. And then we would have 5x is equal to ln of 21,439 with 2 added on. And then we're going to divide the 5 off of both sides. So that cancels. So if you're giving your answer in its exact form before you've even touched the calculator, it is what you see right there. ln of 21,439, that 2 does not get added into there. Then it's 2 divided by 5. Okay, I can't squeeze that in there, but that is the answer that goes right in there. Then you're ready to put it in the calculator. You're going to press in ln of this, add 2, then divide by 5. Okay. All right, so ln of 21,439 plus 2, and then divided by 5. And I got 2.39 rounded to 2 decimal places. Let me calculate that one more time just to check. So it's ln of 2.39. Okay, number 14. Now we've gotten to a different kind of a problem. So in numbers, let's see, I think it was numbers 9, 10, 11, 12, and 13. I took the log of each side. Started all the way when I got to this problem. I got to a different kind of a problem. So numbers 9 through 13, log or ln of each side. I used that in all those problems, all the way through 13. Okay, 14, the reason that this looks distinctly different from anything that I've done is that the word log already appears in the problem. Okay, when you're doing these answers, you want to make sure that your answer comes out greater than 0 if your augment has a variable in it. You want to make sure that you keep that augment, which is just an x, that's all it's made out of, that in the end that comes out greater than 0. So be careful with that, because if you do get something that violates that, then you're going to have to turn around and say that the solution that you did get is really invalid, which would mean there'd be no solution. So what we're going to use here is what we learned about rewriting logs in one of the previous sections. If you want to take this out of log form and into exponential form, you're going to push up the 7, go grab the number that's by itself, that becomes the exponent, and the x goes and takes its place. So the 2 and the x switch sides. The 2 comes over here and becomes the exponent on the 7, and the x goes and jumps in its place and becomes the term that's by itself. Okay, that's how to go rewriting from log to exponential form, which makes it now solvable. So now x is whatever 7 squared is, which is 49. This value is greater than 0, so that actually is the solution. Okay, moving on. Okay, number 15, again, this starts with a log, unlike the other problem. So you can see from numbers 14, which is the one I just did, 14 pretty much all the way to the end. You are starting with problems that already have the word log in it. You're going to want to make sure again that what you give for that it does not make the argument negative. The argument only consists of x in this case. So you want to make sure at the end that your whatever you get for x is greater than or equal to 0. When you have an ln in the problem, the base is said to be e, and it's good to know what the base is because it's the thing that you're going to be pushing up as you rewrite this from log form into exponential form. So push up that base e, putting it in exponential form, go grab the number that's by itself because it becomes the exponent, and that argument jumps over and takes its place. So that's your answer right there. And I believe they'll probably just let you give it in this form. I mean, otherwise you could always just put that in your calculator. You do have a key that has an e, and you could raise it to the 6th power. Okay, let's see. What is the, so this is the exact answer. And you're going to put it in your calculator and get a decimal approximation. Okay, so let's see if my calculator. Okay, so I have e raised to the 6th power. Close that up. I got 403.43. So exact answer, approximate answer. Okay, then this one, same thing. You already have the word log. And by the way, this technique that I'm using where you go from log form to exponential form, that only works, and let's see where this ends up stopping when you have one log, only one log expression. Because on that one log expression, you are pushing up the base. You're going and looking for the value or the variable that's by itself. It becomes the exponent, and then this jumps over in its place. So that's the equation you're solving there. And according to that definition you learned in previous sections, that can only be done when there's a single log in the equation. Okay, and then the number that's hanging off the log, you push it up, go grab the number that's by itself as the exponent, and then that jumps over in its place. Okay, so solve this. On the left you have a 9, on the right you have an x plus 6. Subtract 6, subtract 6, and you have x is equal to 3. That's your answer. Okay, again, you want to make sure with all these answers that this answer is not making your augment negative or 0. See, that's your augment, that whole expression right there in front of the log, x plus 6. If you plugged in a 3 right there, you would not be creating a 0 or a negative, so this is fine. Okay, so the answer is 3. Okay, now next, 17. Again, there's only one log here. And if there's only one log, you can use what I call the push-up method. You're going to push that 4 up. You're going to go grab the number that's by itself. It'll be the exponent, and this will jump out and jump over and take its place. Again, whatever you get, better not make this augment negative, that x plus 2. It can't be anything that's going to make it negative. Otherwise, we've got to throw it out and say no solution. So go in your calculator, type an exact answer in simplified form. Okay, so use integers or fractions for any numbers in the expression. Okay, so they're not actually letting you give a decimal approximation. Otherwise, it would have said what to round to. So if they want an exact answer, that means we're not going to do a decimal approximation. So you're going to go like this. You're going to move this 2 over here. So you're trying to put 4 to the negative 4th together with negative 2, which kind of makes the arithmetic a pain. But this is really 1 over, this is how you rewrite things with negative exponents, 4 to the 4th. Okay, and you can put that in your calculator if you want. Four to the 4th is 256, so this is minus 2, because we're going to put them together if they want an exact answer. So this is 1 over 256 minus 2, which is 2 over 1. And if you want them to have the same denominator, that would be 256. 256. Seems kind of crazy that they want you to go this far, but okay. So 1 over 256 minus 512, 2 times 256, bottom's 256, and then you could pull them together into one fraction. So this would be 1, take away 512, 511 over 256. And that's an exact solution. Unless we have to throw it out, you better check that quick. Will this answer cause that augment to go negative? No, it will not, because you have a positive and you're adding yet more of a positive, so you're not going to let it go to 0 or negative, and those are the things that are forbidden. Answers that make this 0 or negative, which our answer doesn't do. Okay, so that's the answer for that one. Okay, getting to the point where we've done a million examples, but let's just keep going. Let's see. Okay, again, there's only one log here, and therefore I can use the push-up method in order to write it in exponential form. So push up to 2. Get another pencil here, and this will be 2 raised to a power of, go grab that number that's by itself, to the power of 6. And this entire expression swings over and takes its place, 7x plus 5. In the end, we better not be getting an answer that makes this augment negative or 0. We got to protect that at the end, because otherwise it's going to be undefined. So getting into your calculator to get some assistance, you can get the 2 to the 6th, unless you have it memorized. Oops. And that is 64. 2 to the 6 is 64. I'll write that right here. And I'll write the 7x plus 5 over here. Okay, then we're going to solve for x. So subtract 5 subtract 5. At that point, you have 59 is equal to 7x. And then you're going to divide by 7 on both sides, and you'll have x is equal to 59 over 7. Will that harm your augment? No, because a positive times a positive is positive, plus 5, so it's not 0 and it's not negative, so this is fine. Okay, number 19. Number 19, you have all of these numbers hovering around the only term that has a log in it. So this is a problem like numbers 18, 17, 16, where you only had one log in it, but you need to isolate that. You can't have numbers in front of it, no coefficients. See, this had no coefficient, and no numbers being added or subtracted to that log side. So let's clean up the left side. We're going to pull this 8 over here. There's a 54 in front of it. And then you can divide the 54 off of there. And then at that point, you would have ln of x is equal to, and then 6 over 54 is -1/9. And then you can use the push-up method. Once you've isolated that single log expression, then you can use the push-up method. The thing that you're pushing up is the base. Base is said to be an e, so it's e raised up to the -1/9. You're going to need to put that in parentheses, is equal to your x value. Okay, and you want to make sure that when you do get this answer that it doesn't make this argument 0 or negative. No answer is allowed to turn your argument into a 0 or a negative. So when you go and put that into your calculator, if you don't already see what's going on, okay, you could go e, let me clear first, e raised up to a power of, I'm going to put the power in parentheses because it's a negative and because it's a fraction. And I got 0.89. Okay, so let's see. Type an exact answer using exponential notation, and then we're going to give a decimal approximation to 2 decimal places. Okay, so this would be the exact answer, what it looked like before you put it in the calculator. X is equal to e to the -1/9, which at that point you really can't tell whether it violates this because some of you don't know what kind of value that is, but it is a positive value. This just means 1 over e to the +1/9. So when you put it in the calculator, you get 0.89. Okay, and then I'm going to do that one more time. So it's e raised up to a power of -1 divided by 9. Yep, 0.89. Okay, and now you can tell whether or not it's going to mess anything up. See, it's positive, and as long as it's not a 0 or a negative, it's okay. Okay, number 20. Now you get into slightly more complicated problems. What I was saying is that when you were doing, I believe it was like numbers 15 through 19, that you can only do this push-up method where you go from log form to exponential form. That's what we did right here. We were in log form, and we used this same method in 18 and 17 and 16 and 15. You push this up, you go and attach that as the power, and x comes over and takes its place. These two switch sides. And I did that in all the 4 of the problems previous to this one. This is going to turn into that, even though it looks more complicated, because in the last section you learned how to combine 2 logs that are separated by either a plus or a minus. When 2 log expressions are separated by a plus, you can combine them into a single log. That's called condensing your log expressions into a product. So it would be x times 4x minus 1 is equal to 1. Okay, the base that you have here on both of these is a 5. So now you're in a situation, as you were in numbers 19, 18, 17, 16, where you have a single log. And when you have a single log like this, that is when you can use that push-up method, where you rewrite from log form into exponential form. Okay, and then and the way you do that is push up this base, go grab the number that's by itself, and all of this, called the augment, jumps over, takes its place. Remember, in the end, you cannot have anything that makes this augment negative. Okay, so let's continue solving this. We're going to solve 4x minus 1 equal to 5. So we're going to add 1, or you can just use the arrow. So you'll have 6 now on the left, 5 plus 1, and a 4x on the right. Divide by 4 on both sides, and you have x is equal to 2 goes into the top 3 times, and 2 goes into the bottom twice. So you can either report your answer as 3 over 2 or 1.5. Okay, so the solution set is 1.5. Now, does that violate anything? No, because 4 times 1.5, take away 1, is not 0, and it's not negative. And even if you put the 1.5 in there, you would have a positive here. That would be 4, that would be 6, take away, that would be 5. 5 times 1.5, so you're good. Okay, almost there. I know this is a long section, but not much you can do about that. Okay, so I think I'm going to go to number 22. I can't do all of these because it's just getting crazy. Again, you have 2 expressions. You want to combine it into one. Because this is a minus sign, it can be combined into a quotient. So this is going to be a log of x plus 9 Let me check that last problem that I did. Feeling that I left something off. I did. Yep, made a mistake here. I'm thinking about it. That's how delayed my thinking is. Okay, so let's cross that off. Do it again. Okay, so we can go right from here. Log of x. I didn't copy the x when I went into working this out. So it was log of x times 4x minus 1 was equal to 1. And when I began rewriting it, it did have a base of 5. I left off the x. So push-up method. We're pushing up the 5, going and grabbing 1 as the exponent. And when I transferred all of this over to this side, I neglected to take the x with it. So it's all of that comes over and takes the place of the 1. So x times 4x minus 1. So it's actually a little bit harder to get to the answer because you now have second degree. Okay, so now bringing the x in there would be 4x squared minus x. And if you bring the 5 over here, the reason I brought the 5 over here is because I know that I'm going to have to factor because it's second degree. And when you have second degree, you're either going to do quadratic formula or you're going to factor. That's been a gigantic part of this class. So x times 4x, 4x squared, x times negative 1, negative x, and then I brought the 5 here. I'm going to try to factor. If not, I'll use the quadratic formula. So cross those answers out that we had because I copied it wrong. Okay, let's see if we can factor. If you're going to factor, you can either break this 4x squared up into 4x times x, or you can break it up into 2x times 2x. So let's see what works here. If we went 4x, hope you have an eraser because we have to do the guess and check method here, which means we got to mess around with some things. So we could go positive 1, because remember, I keep trying to tell you that when you're breaking something down, the reason it's called guess and check is because you have to guess at where to put the numbers, but then check to see that they give you the proper middle term. Your middle term comes from these two arrows. This is part of it. This is the other part of it. So I already broke up the 4x squared, 4x and x. I'm in the process of breaking up the 5. I chose to put the 1 there and the 5 there. So if I went like this, do these two arrows give me the middle term? 4 times x is 4x. Just check it right over here. I don't want to get in the way of my whole problem here, so I'll do it here. So that would be part of it, 4x, and then that's perfect. See, you would get a negative x out of that. So I did break it down properly, therefore I don't have to use quadratic formula. And now let's go ahead and get the two answers. So significantly harder than the way I just solved it a minute ago when I left this x off. All I transferred was the 4x, and that's why it was an easy problem. But this is really how you solve it. So now I'm going to do two different equations. One of my answers will come from 4x minus 5 equal to 0. I'll get one answer like that. And the other one will come from this, x plus 1 equal to 0. Okay, if I was solving this, I would add 5 to both sides and then divide by 4. So it'll be x is equal to 5/4. And then the other potential answer, because we need to make sure that these things don't violate the augment, would be -1. So are these answers good? So if I was to put 5/4 there, 4 times 5/4 would be 5. 5 take away 1. This one's fine. If I was to put -1 in there, that would destroy this. This is not allowed to be 0 or negative. This portion right in here. Okay, neither one of those can be destroyed by the answer. So this can't be negative, and this can't be negative in the original problem. See, if you put the -1 there, you've already destroyed this. You put a -1 there, it also destroys that one. But if it destroys either one of those, making them 0 or negative, you have to throw it out. So that answer, no good. It violates the definitions and properties of logarithms. And the only answer is 5/4. Okay, so that was that answer. Sorry I had to do that twice. But I didn't realize that something was wrong until I started doing this problem. I was wondering where the harder problems were. Okay, so here we go again. Again, we're going to remember to protect those augments. First, let's apply the property for the minus sign, which is that turns into a quotient. And that is equal to 2. The base here is 5. It's important to know what that base is because it's all part of what's going to happen next. If you want to go from a single log to a non-log situation, in other words, an exponential, you need to do the push-up method. You're going to push up the 5, attach the 2 that's over here, and then all of this swings out and takes the place of the 2. So this comes over here, the 2 came over here and played the role of the exponent on the 5. This is not too hard to solve because you could solve this just doing cross multiplication. So the 5 squared is 25, and then you have this rational expression on the other side. And you can go 25 times x minus 5. And then you have an x plus 9 on the other side. Then bringing the 25 and distributing it through, you have 25x minus 125. That's equal to x plus 9. And if you continue with that, you can bring the x's over here. Minus x, you would have 24x. And then you could bring the negative 125 over here by adding 125 and adding 125. And that would give you 134. And then you could divide by 24. And reduce. Okay, so the top divided by 2 is 67, the bottom divided by 2 is 12. So that's your answer. And then let's just make sure that it really is an answer by making sure that it doesn't mess up anything here. So 67 divided by 12 is it's approximately 5.58. So when we see if it messes up either this argument or this argument, it doesn't. This is, you know, I'm just thinking about it, even though I'm going to give it as 67 over 12, what its decimal approximation is, just so I can figure out, hey, am I creating a 0 or a negative with this number? Because if I am, this one answer I got is no good. So let's see, 5.58 plus 19, good. We're good right there. 5.58 minus 5, no, you do not get a 0 or a negative. So this does not mess up either one of those. So 67 over 12. Okay, then let's see. Let's go to about 24. Jump around a little bit. There's just too many here. Okay, so let's see. We have log of x plus 6. And then on the right side, we can put those together. And that's going to be log of, let's see, there's a plus sign in between those. That means that used to be a product. So starting with number 23, you are into different kinds of problems now. There's no way that you're going to end up from 23 on with only one log. Whereas everything that I had up here, I had one log, and therefore I could go into a power expression, an exponential expression. When you have one log on each side, it's actually kind of easier than this side. Log expressions can only be equal if their augments are equal and their bases are equal. Well, if these are both logs, their bases are both 10, so that's good. Check on that. And you finish the problem by making sure that the augments are equal. So essentially, you're just dropping these logs and continuing the problem by figuring out what would make these augments equal. Okay, so here you would have to subtract x. You would end up with 6 is equal to 5x. You would divide by 5. And you would end up with x is equal to 6 over 5. Okay, does that mess up any of the arguments? You got to go back to the original. It doesn't mess that up. A positive plus a positive, good. Makes that positive, and that you can't change. So this is fine. Answer is 6/5. Okay, moving to the next page where there's more of that sort of problem. Here you have two logs on one side, so you can combine them based on knowing what this plus sign means. It means that they used to be a product. So the left side would be log of x times x plus 6, whereas the right side is log of 27. Okay, when you have the same kind of log on each side, same kind of base, then you can essentially just get rid of the logs, because these expressions can only be equal if they're the same kind of logs and that the arguments are equal. So we want all of this represents the argument. Okay, so I want to know how to solve x squared plus 6x equal to 27. It's second degree, therefore you're going to have to bring everything to one side. By the time you bring this over here, it would be negative 27. And you're going to try and factor that if possible, because it's easier than doing quadratics. So break up the x. This is pretty easy though, and that's because there's a 1 in front of the x squared. Those are easier. So I'm going to do a positive 9. That'll give me 9x, part of that middle term, and then a negative 3. So positive 9x minus 3x will give me the 6x, and then it'll also give me that back number. Okay, these numbers are always numbers that multiply together to give you that back term, but there's always several possibilities for doing that, so you want to find the pair that will create that middle term. That's why you have to check on the middle term. Okay, if you were to make an equation out of the first factor, which is always what you do when you're solving second degree, you continue until you've gotten answers for these first degree equations. So I got one answer of x equal to 3. Don't know if it's really an answer. And then this factor gives me an answer of negative 9. Again, I don't know if either one of these are truly answers because I still need to look at them with respect to the original problem, making sure that they don't make any of the arguments negative or 0. It doesn't do that to this. Doesn't make it 0 or negative. Doesn't make this 0 or negative, so this one's good. And then the negative 9, right away it makes that first expression negative. It is no good. Throw it out. So the only solution here is 3. If none of them end up working, then you just say no solution. Okay, so 26. In number 26, again, so this will be probably like the fourth problem where I started off with 3 logs, but condensed one of the sides into a single log. Because you can put those two expressions together. Let's see, there's a plus sign. That means that it used to be a product. So it's a product of x minus 8 times x plus 1. And then over here it's x minus 24. All right, so for these two logs to be equal, they're augments. This is the augment of the log on the left. This is the augment of the log on the right, natural log. So we're only working with the augments now. Oh. Okay, this one needs to be FOILed out. So it's x squared plus 1x minus 8x. No shortcuts for this foiling. And then negative 8. And then over here it's x minus 24. So now since that second degree is not going away, you're going to get everything on one side. So it's x squared. Put those two together and you have minus 7x, but you're bringing this x over here as well. And there's a negative 8. When you bring this over here, it's positive 24. So everything's on the left side. Okay, we had a negative 7x. We brought this x over here as well. We had a negative 8. We brought the negative 24 over here as well. Now clean it up further. So it's x squared. Negative 7 combined with negative 1 is negative 8x. Put those two together, and then this combined with this would be 16. Positive 16. Okay, when you go to get the answers, you're going to have to factor to try and do that. Break up the x, and then let's see, negative 4 and negative 4 would work here. That times that is 16, but when you add those two numbers, you get negative 8. So that'll achieve the middle term. That's another way you can check the middle term. Okay, so if you take either one of these factors, since they're twins, you're going to get x equal to 4. But is that an okay answer with respect to the augments here? Let's see. No, it is not. See, when you put a 4 in that first one, 4 take away 8, it results in a negative number. 4 take away 8, you end up with a negative. That's no good. So this is no good. I mean, it's okay there, but it also ruins that one. So this is not a number that's good. You're not looking at whether this comes out negative. You're looking at what does it create when you plug it in here. Does it create a negative or a 0? Because if it does, you have to say no solution. That was the only answer I got. Only answer I got didn't work. Okay, moving on to number 27. Okay, number 27. We have 5 to the 3x times 5 to the 3x. So when you are multiplying exponential expressions and their bases are alike, you can add the powers. This is the power rule. And so this would be adding up these exponents when multiplying like bases. You add the powers. It's a power rule. And then on this side you had a 25. So this is, whoops, I'm already thinking about that. So it's 5 to the 6x. And then over here, this is 5 squared. I'm rewriting the 25 like that because I'm getting ready to use what I used in the first 8 problems. If the bases are the same, the only thing that you need to check further is that the exponents are the same. And then continue solving. Divide by 6, divide by 6. And you get x is equal to 1/3. Okay? Here there's no violating the arguments because you don't have log expressions, so there's no worry about it being undefined, unless you come up with some number that